Good evening, everyone. Myself Nilmoni Karak, a research scholar at IIT Kharagpur, and I am the PMRF NPTEL TA for the course Fourier Analysis and its applications. And yeah, which is taught by Srinivasan sir. And okay, so today we will see. So what we have seen last week. So compact operator, self-adjoint operator, and connection and its connection with boundary value problem. And several examples we have seen for a compact operator and like Volterra operator, but which is not self-adjoint. And yeah, so uh, in this week we will start with open mapping theorem. Okay, so first we recall some content from last week, and then we will solve some problems related to this week content, and which will help you to solve your assignment problem. Okay, and first let us start with open mapping theorem. So this is sorry, week 10, right? And okay, let us start with open mapping theorem. This is very known in function analysis, right? As well as you have seen this in complex analysis. Very famous. Actually, open mapping theorem we study in function analysis to get a homeomorphism between two spaces. Okay, two nonlinear space, or can set or two matrix spaces. Okay. So first, in general, we take let okay, consider first let f x to y. So x y are two matrix space. Okay, two matrix spaces, and f x to y is a map. Okay, so is a map. So you know when it is continuous in matrix space, or you know the topology definition. Okay. So in matrix space we have distance, but in topology in general we don't have distance. So there is one open map definition, or you can say like open set definition for continuity. So if x to y is said to be continuous on x, obviously here if uh, so this is both sided actually. If inverse O is open in X, actually this may not be whole set, right? So if inverse O is open in X, which is subset of X, which is open in X for every open set, no, whenever uh, O is open in Y. So it is given actually. So O is open. If O is open in Y, then F inverse O is also open. If this implies, then F is continuous, and vice versa. Okay. So suppose you consider f x to y is bijective map, bijective continuous map. Then can we say about like can we talk about f in continuity of f inverse, whether f inverse is continuous or not? So for that we study open map theorem, of open mapping theorem. So yeah, so you know if f is continuous, bijective, and then if f inverse is continuous, then x and y are homeomorphic, right? So you can recall. So uh, now we come to our definition. A map f x to y. So similarly, we can talk about closed map. Okay. So there is nothing like to say differently. Okay. We can talk about it simultaneously. Okay. So said to be an open or closed map if whenever O is open or is now respectively closed in X, the set f of O is again is also open, is open or respectively closed in Y. Okay, so this is called open map or closed map. Okay, but this is not open mapping theorem. Okay, so this is the definition of open map. Okay, so there is a theorem uh, about this why we study open map. Okay, so a bijective continuous map f x to y is a homeomorphism if it is open or closed map. Okay, now come to open mapping theorem. This is a healthy theorem. So and yeah, many counterexample like uh, many counterexamples arise from this theorem. Okay, so let H be a Hilbert space. So in general, of course, we can like we can state open mapping theorem for any nonlinear space, but here we just specifically study for Hilbert space, right? And T H to H be a surjective continuous linear map, then T is open mapping. Okay. Uh, okay. Next, we have revisited Volterra operator. We have seen 0 is not an eigenvalue of Volterra operator, and then actually there is no eigenvalue for Volterra operator, and we then studied for about spectrum of the Volterra operator. So now I'm skipping this and immediately I'm going to weak convergence of a sequence. So weak convergence. Okay. So first, you know norm. What is norm convergence? So suppose you have a sequence Vn in a Hilbert space H, then Vn is said to converge to V if so to V norm, of course. So I am talking about norm convergence. If this norm Vn minus V goes to 0 as n tending to infinity. So but for infinite dimensional nonlinear space, always it is not useful. So for this, we introduce some much weaker notion. So that is called weak convergence. Okay, let us see what is the definition of weak convergence sequence. So a sequence Vn. So this is sequence of vector, of course, in Hilbert space. In H, so this is of course Hilbert space. Whenever I write H, you should assume it is a Hilbert space. Is said to converge weakly to V if for this is important every W belongs to H is Vn minus V comma W goes to 0 as n tending to infinity. Okay, and it holds for every W in H. Okay, and here V is called weak limit of Vn, and also one thing, the norm convergence by Cauchy-Schwarz inequality, one can check the norm convergence immediately implies this weak convergence. Okay, okay. Uh, for example, if we consider this Hilbert space L2 minus pi to pi, then you cos nx and sin nx. Okay, this sequence are orthonormal, right? And this sequence converges because uh, converges to zero. Uh, this sequences converges weakly to zero. But how? Because so these are orthonormal, right? And for every, so just consider for every f in L2 minus pi to pi. Okay, so the integral minus pi to pi ft cos nt dt. So this limit goes to zero, and similarly minus pi to pi. What is the argument here? Sin nt dt. This goes to zero as n tending to infinity by Riemann-Lebesgue lemma. Previously we studied. Okay, Riemann-Lebesgue. Yeah, Lebesgue lemma. So UE, right? Okay, lemma. Okay, so this is the norm, right? So this is the not norm. Sorry, this is the so yeah. So cos nt minus, sorry, minus 0 comma f. This is the inner product for L2 minus pi to pi. Okay, for this Hilbert space. And so this is one immediate example. And if you try for another example, just you can take small L2 space. So here, if you consider this type of sequence, so yeah, 0, 0, 1, 0. So 1 is in nth position. Okay. So for this case, this en minus 0 for something like e in L2. In for this case, so yeah, the inner product is usual product. So this goes to basically zero, and this is your goes to zero. And so for this case also en quickly converges to zero. So this is also an orthonormal basis. Okay. Uh, so now we see what is weak and norm convergence theorem. This theorem, weak and norm convergence theorem. Okay. So suppose Vn, so this is weak convergence. Vn is a sequence of vectors in a Hilbert space H converging weakly, then the sequence is non-bounded. Yeah, so we will like see yeah, this is how this is needed in like assignment problem, and the proof is very simple. So bounded, non-bounded means that is, you can say there exist constant. Obviously, this should be positive, such that this Vn less equals to m for all n belongs to n. So see, so here you can use mm, Banach-Stener's theorem. Okay, so you can consider a map. Okay, Tn and from H to C, and then using Banach-Stener's, so you can like you can argue this sequence is non-bounded. Okay, okay, so we will see later. Okay, so and the second theorem is, suppose Vn is a sequence in H, the Hilbert space, which is non-bounded, then there is a subsequence converging weakly. So this is like converse part of the previous, so sorry, this previous statement. And so Vn, if Vn is non-bounded, then the sequence is non-convergent, weakly non-convergent, but no. So there is a subsequence that converge weakly. Okay. Okay, so for proof, one can check lecture video as well as lecture notes. Okay, so to prove the second part, one can use Banach glue uh, for separable Hilbert space. So all are all we are studying for to actually for stating spectral theorem, right? So next theorem, suppose H is a Hilbert space and Vn is a sequence that converges weakly to V. Assume that Vn is norm-convergent. No, so not assuming. So we are assuming this norm Vn converges to norm V. Then we have Vn converges to V in norm. Okay. Now state the spectral theorem. Suppose th to h is a self-adjoint operator on a Hilbert space, and tvp is real for all p belongs to h. And second, eigenvalues of mm, t are real. Of course, if they exist, and the corresponding the eigenvectors corresponding to the eigenvalue, to distinct eigenvalues are mutually perpendicular. Okay, so the proof you can check from lecture videos as well as lecture notes. And yeah, next theorem. So if you have compact self-adjoint operator, so mm, can you give a eigenvalue precisely? Okay, of t, of course. So th to h is a compact self-adjoint operator on a Hilbert space. Then so tvp is an eigenvalue of t and is attained at an eigenvector of h. Okay. The proof is very um, very easy and elementary proof. Okay. Now we will see invariant ortho complement. Okay, so suppose that bounded. So H is a Hilbert space. T H to H is a self-adjoint bounded operator on H. We say that Y is a T invariant subspace if it is a vector subspace and TV belongs to Y. So this is basically a invariant subspace definition. So interesting fact is that if Y is a T invariant subspace H, then also T invariant Y perp is also T invariant. As a proof is simple, suppose Z belongs to Y perp, and we have to show TZ to show TZ belongs to Y perp, right? So Z belongs to Y perp means so one thing this Ty belongs to Y, right? Because Y is as Y is invariant, T invariant. So Ty in Y and Z in Y par. So Z comma Ty is 0. Okay, and this imply Tz comma Y for all Y belongs to Y. So this imply your Tz belongs to Y par. Okay, now existence of an orthonormal basis of eigenvectors. Suppose Th to A is a compact self-adjoint operator on a Hilbert space, then there is an orthonormal basis of eigenvectors of H and each non-zero eigenvalue of T has finite multiplicity. So this props yeah, comes from John's lemma, like you know. So the existence comes from John's lemma, and you can look at this proof. Okay. Weighted L2 space. L2 spaces. So let rho R be non-negative continuous whose zeros or be set of non-zero measure sorry non sorry measure zero say set of measure zero. Then L201 denotes the set of all F01 to R such that 0 to 1 and here we can define inner product like this. Okay, and with this L2 row 01 is a Hilbert space, and proof is similar as the usual L2 space. with some cosmetic changes. And yeah, and the this space actually is needed to study this Sturm-Liouville problem. Y dash plus rho lambda rho y 0 y0 equals to y1 equals to 0. Now Sturm revisited. Um, okay, so consider this space instead of L2 space. We consider this space L2, and this is a mapping. This is the operator, and compact operator, of course, and this is given by tfx 0 to 1 kx comma t ft root t dt, and this is compact. Okay, or not always when txt is continuous on the rectangle 0 1 cross 0 1, unit rectangle actually, and also t is self-adjoint when kt equals to ktx. And so proof is similar like as L201 for the case L201, and uh, so now we can study Sturm-Liouville problem, uh, and we can transform the Sturm-Liouville problem to eigenvalue problem for a compact self-adjoint operator. And so for this Sturm-Liouville problem, and the eigenvalue is countable set extending infinity, and each eigenvalue is simple and eigenfunction on complete orthonormal basis, uh, and each eigenfunction can be written as like a Fourier series f equals to summation n equals to 1 to infinity c and yn are eigenfunction. Okay. Means not each eigenfunction. So every member for L2 row 01, this can be written as okay. Okay. Mm, okay, now for application parts, we will see next class. We'll see in the next class, and now let us solve some problems related to these topics. Okay. Okay. So I'm coming. Okay. Uh, okay. So first problem. Let X and Y be two metric spaces, and X is compact metric space. Compact. Also, f(x) to y is continuous function. Then f is open. Number two, if f is bijective, then f is homeomorphism. If f is bijective, then f inverse is continuous. F is closed. Okay, let us solve one by one. So first, okay. So first is saying whether F is open or not. Actually, this is wrong statement because you consider x01. This is compact, right? In our usual metric, okay, of course, usual. And F01 to R and fx, just take constant function. Then F singleton 0. So, sorry, open. So this is open set, which is not open in R. So F is not open. Okay. So what about second? Okay. A bijective, then F is homeomorphism. So to show homeomorphism, so any bijective continuous map, if it is open or closed, immediately it is homeomorphism. Okay. And bijective, yeah, immediately why? So F inverse is continuous, then also this is homeomorphism. So 2 and 3 simultaneously correct or incorrect. Okay, and actually if is closed, this is also correct. So let us see how it is correct. So if closed, let us uh, try to prove it. Since X is compact and subset of X is closed, then A is compact in a metric space. This is true fact, right? If closed in a compact space, then it is compact. Okay, and let A subset X be any closed set, closed subset of X, then A is compact, and here F is continuous, right? We know that continuous image of a compact set is again a compact set. Okay, so f of A is compact in Y, and Y is a matrix space, so f of A is closed in Y. So F is closed map. So 4 is correct. And since F is closed, so bijective plus continuous plus closed F is homeomorphism. So this implies F inverse is continuous. So 2, 3, 4 correct. Okay. Now problem 2.
Unknown caller.
Hello. Yes. Okay. Okay. Next question. Let H is a Hilbert space and T H to H be a B. Self-adjoint operator. Then purely imaginary sorry for some uh, if eigenvalues of T exist, then they are real. Actually, this is a spectral theorem which we just have studied. Okay, if it is compact, then not an eigenvalue of T. So, so first question is basically you have a self-adjoint operator PVP. This is always real by spectral theorem. So this is TV comma V. For real case, this is obviously real. For complex case, this like so TV comma V is always real for all V belongs to H. Okay, so one is wrong. And what about two? Lambda means eigenvalues are always real. Yes, this is just spectral theorem. So suppose this, and this is lambda v square. Again, this is v comma tv. This is tv comma v bar. From here, lambda bar v comma v. The lambda bar. Sorry, square. And compare this and this. We will have lambda equals to lambda bar, and so lambda is in R. And 3 is we have seen theorem. So due to this that theorem, this is true. And 2 and 3. So 4 is not correct because 3 is correct. And the theorem is we just stated before. Yes, this theorem. If TH2 is compact self-adjoint operator on a Hilbert space, then this is an eigenvalue of T and is attained at an eigenvalue of H. So you can eigenvector of H. So you can find it from lecture notes. Okay, the proof. Okay, so let us see next problem. Problem 3. Consider the Volterra operator. Spectrum of T. So 0 is eigenvalue, 1 is eigenvalue, 0 is in the spectrum of T, and 1 is in the spectrum of T. Which one is correct? Which one? Which are the true? Okay. Mm, let us check. So this is Volterra operator, right? So T of fx 0 to x f to dt, right? Uh, Suppose 0 is an eigenvalue of T. Then there exists non-zero L2 function if such that equals to 0, 0 to x for all x belongs to 0 to 1. So from here x to y ftdt equals to 0 for all x y belongs to 0 to 1. X less than y, and ftdt equals to 0 for all measurable subset of y of 0 1, and this is just f is 0, and which is contradiction. So 0 is not a, again suppose 1 is an eigenvalue of t, non-zero L2 functions of f. So tfx equals to fx, right? So 1 is an eigenvalue. So this is this implies fx. Now differentiate both sides with respect to x. Then we have f of x equals to f dash x, and this implies f of x equals to c time e to the power x. C not equals to 0. So this does not satisfy this, right? Because if you put then 0 to x c to the power t dt, this is actually c e to the power x minus 1, and the right hand side is nothing but c to the power x. Okay, and this is not true, so which is contradiction. So 1 is not an eigenvalue. Okay, 3. What is the option 3? Option 3 is 0 is in the spectrum of t. Okay, so first of all, let us see what is the definition of spectrum. We know that uh, lambda is said to be in the spectrum of t if at least one of the following holds: t minus lambda I is not injective, t minus lambda I not surjective. So basically, t is not invertible. So in the last week content, so we have seen in for Volterra operator T minus lambda I. This is actually not surjective for lambda not equals to 0. Okay, for any lambda not equals to 0, and for lambda equals to 0, uh, so this is in the spectrum. Is in the spectrum. Suppose G is in L201, so TF equals to Z for some F. So this implies 0 to X, FPDT equals to Z, Fx equals to G dash X, and for any constant function G, for any constant function G, F is always 0. Okay, so actually, yeah, so when this is not satisfied, so if we consider like this, 1 and 0, not this is 2, when 0, 0 less equals to x less than half, and half less equals to x less than 1. Okay, gx. So this is like, so we don't have ape, right? We cannot find, we don't have any ape for this T. So this T is not surjective, and T minus 0 time I is not surjective. So 0 is in the spectrum of T. Okay, problem 4. So 0 is the only mm, so yeah, so 0 is the only spectrum. So the spectrum set is basically is a singleton set which contains 0. Okay, and for a Hilbert space, the spectrum set is always non-empty. But this is an example where the spectrum set is singleton. Okay, this is very special example. Okay, suppose T is a compact operator and S is bounded operator on an infinite dimension Hilbert space, then Ts is not bounded. TS is compact, but ST is not. ST is compact, but TS is not. Both ST and TS are compact. Let us solve this. Actually, by the definition of compact operator, here TS and ST both are compact. Okay, and compact means this bounded, so all are incorrect. Remaining three options are incorrect. Okay, let us solve. So how this is a true actually, and so you know, right? An operator TH to H is compact if it sends any bounded set to a pre-compact set in H. Pre-compact means relatively compact, so the closure is compact. Okay, not necessarily the set is compact. So so that means pre-compact means every sequence has a convergent subsequence. So let Xn be any bounded sequence in H. So T is bounded. What is given actually? T is compact operator, H is bounded, right? But compact is bounded, so T is bounded. So Txn is also bounded in H. And since, oh, okay. Sorry. This is S. This is S. Since T is compact, okay. So Tsxn has a convergent subsequence, and this implies Ts is compact. What about St? How this is compact? Similarly, let Xn be any bounded sequence in H. S is compact, so Sxn has, sorry, T is compact. So Txn has a convergent subsequence Txn k, that is Y. Say, and now your S is bounded, so that S is continuous. So STXNK is converges to SY, and so this implies what? STXNK as a TN, not TN, XN as a convergent subsequence. ST is compact. Hence we're done. So STTS both are compact. So problem, what number of problem? Problem 5. In a Hilbert space, a norm-bounded sequence always has a norm-convergent subsequence. Weakly convergent sequence is norm-bounded. A norm-bounded sequence always has a weakly convergent subsequence. If un goes to u weakly, then norm un goes to u and then to infinity. Let us solve. So first is saying that a norm-bounded sequence always has a norm-convergent subsequence. This is false in general, because very simple. Is false in general. So it is true only in finite dimensional nonlinear space. So take this L2 n equals to 0, 0, 1, 0. So this is basically your where 1 is the nth position, is in the nth position. Okay, 1 n is norm-bounded, but this is norm-bounded, right? So, but for any mn belongs to n, m not equals to n, en minus em, this is root 2. Okay, so this means en is not Cauchy. So cannot have convergent subsequence. Okay, so this is not true A weakly convergent sequence is non-bounded. This is exactly we have studied in theorem. So this is true. This is actually can do by Banach-Stein's theorem. Uh, Let xn weakly x in H, right? So you have weakly convergence. So xn w to xw for all w belongs to A. Now define Tn w equals to xn w for all n, and each Tn then is bounded, right? Bounded linear function. Okay. Uh, because this is convergent, so this is convergent means this is bounded. So this is bounded. So bounded, and that means for all n. So soup n belongs to natural number. Tn w is infinite. So by Banach-Stein's now, Banach-Stein's soup, this is infinite. In H, this is clearly true, right? And so this soup, so non-bounded. So that's why this is true. Next is a non-bounded sequence always has a weakly convergent subsequence. So this is also true by Banach Aloglu theorem. Okay, so this is true. So consider the dual space of H. This is H star, and since any Hilbert space is reflexive, the Hilbert space is reflexive. So H to H star. So unit ball in H star is weakly compact, star compact. Okay, so since reflexive, so unit ball in H is weakly compact. Now Banach-Aloglu theorem. So this Xn is bounded, lies in a ball, and this implies it has a weakly convergent subsequence. So this is true. And if UN converges to you weekly, no, this is not necessary. Necessary. Okay. So just consider any you consider H equals to L2 space, L2 minus pi to pi. So FT. This just cos NT, right? This is orthonormal. Okay, so FT cos NT. So this, uh, sorry. this cost actually goes to 0 weekly as n tending to infinity. So ft cosine t, this is minus pi to pi, this is 0 by Riemann Lebesgue lemma. Okay, so and so that means basically so the reason the weekly convergence, so because of this, because you know cosine t minus 0 f equals to 0 by f goes to 0 actually goes to 0 as intended to infinity, so by Riemann Lebesgue lemma. But cosine t equals to norm minus pi to pi cosine t square dt. So this is half 2 cos square nt minus pi to pi 1 minus cos, so 1 plus 2 cos nt dt. So this is this will give sign, so that is 0, and this t so, so half into 2 pi, this is actually pi, so not equals to 0, right? So not to 0. So cosine t not 0. Okay, I hope it is clear. So it is not true. Mm, and this was the last problem for this season. Now we will meet uh, next uh, Sunday at the same time. Maybe if possible, I will take one extra class in between. Okay, you will just you will be informed before the class. Okay, okay. Thank you.